Any questions about anything up to this point? Let's just have that up right. I mean, the screen's down, I should say.
One of the guys earlier said that they heard you say that, like, for the correlation functions, it can't be round, but I don't. For, you know, that like problem 6-1F.1, where it's like one of them's not symmetric, one of them doesn't have the peak at 0, one of them has the vertical jump. They were like, well, it can't be the third one because I thought it couldn't be round. And I was like, why can't it be? But they said that they heard it said in class, so I don't know.
You talking about a half sphere?
No, just like the
Round?
it's just smooth
That's
instead
a
of
half
being.
sphere.
He's talking about this one.
Sure, that's legal. It's the part C?
Yeah,
That's-
they were-
That's legal.
Yeah, they were. I don't know why they were saying, but they said that they heard it said in class. So
Who?
I don't remember somebody.
Here? Did anybody say that?
I thought B and C were right, but some people thought it said that it couldn't be round.
Which one?
I thought B and C were right, but then they told me that you couldn't have the drop off at the end because that was invalid.
You can't have any straight,
Yeah,
vertical
no
edges,
straights.
no vertical
Yeah,
edges.
No vertical edges and no flat tops.
Yeah, and you can't have, right, the maximum has to be at the order, at
Yeah,
0.
at 0.
That's right. That's that thing's up. First, I'll make a couple comments. I'm going to use, I've got some PowerPoints I've got made on this. It's something we'll talk about. There was one problem. You both asked me about 6-4 or 6-3.4, I think it was. And see, we're going to be doing things in the spectral domain, but I'm just going to tell you one thing about this. Right? So if you have an autocorrelate, any function, we're just going to go say x of t, and Riley, are these the good markers?
No, you're.
I found some in my office that work where we found, and he brought it. We actually came up to get them because I forgot to give them to him. Oh, I'm glad you did. All right. So we're going to do this just as a review. Remember, he has in the PowerPoint set of Denny's, he has a sets of functions here, the transfer function, or the Fourier transforms, and this is kind of important too. So there's one thing in the spectral domain, anytime you have a Fourier, or a transform of an autocorrelation function, it can't have negative values. Do you follow me? Now, let me give you an example. So, first of all, the delta t is one it's non-realistic as something that can actually happen, but it serves a purpose. And you can approximate this by a Gaussian curve. If you think about this and let the standard deviation go to 0, it'll become just a needle point. But in the spectral domain, you get a constant right here. It's just flat across the bar, and it's just simply 1. I mean, when you see 1 there, it means for all values of omega, it's 1. Do you follow me on this? It's why it's going to have. You're going to have spectral components out to infinity, theoretically. The next function that they talk about, that I use the symbol p tau of t, but it's also called rect t of tau, t over tau. And I'm going to draw this one up. This is kind of important because we're getting to points where we'll build functions that can or can't be legitimate autocorrelation functions in the time domain. See the spectral domain, because in the spectral domain you can tell right away if it's legal, or I should say you can definitely tell if it's illegal, if it's got negative values. So that function, we talk about a rect t that looks like this. From minus tau over 2 to tau over 2 with a height of 1, and this would be, you can call it the rect t over tau. I usually use this symbol, but I think this is more common from what you had in signals and systems. That transfer function for the rect t is simply tau in the omega domain, tau times the sinc of omega tau over 2. So if over this domain, what that looks like in the omega domain is this. It has a peak value of tau, and it basically does this. It's a sinc function. Y'all follow me on that? Everybody? If you take one look at that in the frequency domain, the omega domain, you can see, this is the omega domain out here, that has negative values, right? It can't have negative values if it's a legitimate autocorrelation function. Now, cross-correlation function, it can't. Don't worry about that. We'll talk more about that in a second. So that's one. Another one, and these are the pairs you should know. And this is, I use the symbol of the triangle function of t over tau. Or really, actually the way it's usually done is this. And I don't know what you're used to, the symbolism. You'll see something like that. It looks like a triangle. It's actually pretty flat. And you'll see a sub tau of t, right, like that. And that function is 1 minus 2 magnitude of t over tau times the rect of t over tau. Y'all follow me in this class? Now that defines an actual, this shape, the triangle shape, and that looks like this. And this is the one in the book. So the triangle function looks like this. It has a height of 1 minus tau over 2, tau over 2. Over here, the transform of that, by the way, these markers are starting to die on me. I'm going to find some marker. We used to have good markers, but I think all these things are literally from the COVID era.
Mm-hmm.
They've been stashed away and they're just not working. But over here, what that will end up being, I didn't put it here. Some of you remember this. This is going to be tau over 2, but it's a sinc squared of omega tau over 4. Do you remember that function? Anybody? Well, that means the height here is going to be tau over 2, and it's going to look like this. That's strict positive. Are you with me? Now, I'm going to mention a couple of things that are important to see. If this is, this is a triangle function, and that has no negative components, right? As a matter of fact, we can look at either domain. This has a peak at the origin, has no straight lines. If you look at this function right here, it's symmetric about the origin. Over there in the spectral domain, no negative values. It checks the boxes in both domains. It's legit. Something I'm going to tell you about that you should pick up on, but oftentimes you don't, is, let's look at the top one. It'll be easier to see. For this function right here, if you ever saw this, and I'm not going to give this to you today, but I want you to just be attentive to this because I might ask something about something that's related to this on the final. If I just drew that out there and I'd say this has a value of 5 and this has a value of minus 5, and I took a look at that as the actual, I say this is the spectral signature. We could do it for this one, and we will, but I want to start with this one, it's easier. If you see just that, that's 5, and say this height right here is 2, right? Now, if you look at that, we know something. We know right away, if that height's 2, and this is basically the transform of the rect function. For the rect function, that means this would have to be scaled by 2. You follow me on that? In order to get a height of 2 over there. Follow me? Well, actually, there's more to this. I better do this the right way. This function is tau times the sinc of omega tau over 2. That's not quite true. This height, whatever it is, and if I made this, I'll make it 2. it means tau right here would be 2. I said that wrong. You follow me? Everybody understands? I'm trying to make sure I do this. Now that we have tau, I can put a 2 in here and erase the 2 there, right? Basically, I have that. Follow me? Now, if you take a look at this, and actually, I gotta be a little careful about this. Let me do one thing. I put too much information. If that has a height of 2, actually, let me go back for 1 second. Try not to. I'm gonna do this. This is tau times the sinc of omega tau over 2. And I want to do one other thing. Over here, I'm going to make this an arbitrary value, a scaling factor, and I'm just going to call it A. So over here, there would be an arbitrary scaling factor of A here. Now that should make sense. I was trying to show you how to actually find the values in this sinc function and go back to the time domain. That's my goal on this one. Do you all follow me on this? I'm not trying to confuse you, but I kind of led you astray. If you take a look at this, the first thing you can say is A tau would be equal to the height at 0, 2. Do you agree with this, everyone? But that's not, now we're not quite done. This is an important quantity too. And if you look at this, you always look at where it goes through 0. And if this value is 5, and this is minus 5. Now you know the sinc function, this whole thing could be defined as A tau times the sine of omega tau over 2 divided by omega tau over 2. Y'all follow me on that? I mean, do you remember that the sinc function is sine x over x? Does everybody follow me on this class? Now, if you look at that, here, we're interested in where the first 0 is of that. Because this, I gave you this value of 5. Follow me? So when is a sine 0 after 0? The next 0 is, think about it. It's 0. Sine of x is 0 at x equals 0 and at x equal pi, right? Not pi over 2, pi over 2, it's 90 degrees. The sine of 90 is 1. So at pi. So now you can say that omega tau over 2 is equal to pi, or 2 pi divided by tau would be omega. You all follow me on this? Right here? Now, if it goes to 0, omega equals 5, then you can get tau. So you can get tau equals 2 pi over 5. And if you do that, basically, you've got tau here defined as 2 pi over 5. It means you can get A, which is going to be 2 over tau, or 2 times 5 divided by 2 pi, or really, that would be 5 over pi would be the scale factor. I'm just doing this one time to show you. Basically, if you're given this information, and we could do it for this one's easier to see, I think. If you're given this information, the height and the first 0, you can go back, and you know it's a sinc function, literally. It would have to be, in some way, shape, or form, clearly identifiable as a sinc function. Then you can go back to the time domain, and you could get this function, right? You're just going back and forth. Here's where it gets a little confusing. Remember, I'm using the symbol tau for the width, right? But in fact, what we'll have for autocorrelation functions, we'll have this. We're going to have an autocorrelation function, maybe, but the functional form will have an argument of tau, not t. This is one of the things I just want to mention. So when you do the Fourier transform of that, you're actually transforming from the tau domain to the omega domain, not from t. Follow me? So then all these things, and we'd have to get another symbol. This would be like, let's call it tau 1 here. And then this would be the symbol for the autocorrelation function, tau. And this is tau 1. And over here, this is really going to be tau 1. And so forth. So I'm telling you that you at least have to be familiar how to fit the form to go either from call it the time or temporal domain to the frequency domain. And these are some of the characteristic ones. So now I make my point here. This is the spectral density, spectral energy density, or power density, sorry. And I'll call it the function x of omega. And that's what I'm going to talk about next, the spectral power density. These are the relationships from either domain. I'm just bringing this out because you're probably a little rusty in this. You probably remember this one, right? And there's a few others to remember. If you have e to the minus a magnitude of t, that one is what? Isn't that 2a squared over omega squared plus a squared? Do you remember at least vaguely that? Now, a good question you should have in your mind, will I provide Fourier transform pairings? I will. I mean, I'm not going to expect you to know all of them. You should at least be familiar with some of them so you know how to figure things out. But now, the next thing I'm going to do is the power spectral. I'll just mention this right here now. I'm saying a lot about this stuff. And I know you got a quiz if you're interested. Otherwise. So, when you did basic circuits, all the stuff you did, you found, I'm trying to do this in a way that makes sense. You always found the relationship that if you had voltage V of t, you actually didn't go into the transform domain, to the omega domain. You didn't do I don't think you used Laplace or Fourier transforms in basic circuits, did you? You don't usually. We used to use Laplace transforms to solve differential equations, but I don't know if you even did that in circuits. I don't think you do anymore. You used to. But however, in circuits, you knew that voltage and current are related either by a differential equation like L di dt would be the voltage across an inductor, or an integral like C dV dt would be the current through a capacitor, or it would be an absolute simple relationship that V equals I times R, where R would be the resistance. Now power was always related to either I squared or V squared. Do y'all remember that? Always. And when we're going to talk about spectral power density, and we don't talk about spectral energy density, there's going to be a relationship, and I better just show you on the slides, but you're going to find out that autocorrelation function. Remember, for the autocorrelation function, when the argument of tau was 0, that was the mean squared value. Do y'all follow me on this? Well, the mean squared value is a squaring operation of x of t, and if x was a voltage, it would be the square of the voltage. And if you take that value, and then if you think about that, would be akin to a square of a voltage, that is related to a power term. Now you're going to see the exact relationship, but I'm trying to just point out one thing. If you have any kind of a function that is akin to a voltage or current, you have to square it to get power. This is the important point I'm trying to make. I'm not doing a very good job right here, but I'm going to put this PowerPoint up. And this has got a bunch of information. And I didn't put it on OneNote yet, but I'm going to. most of your classes use PowerPoint in engineering? I'm just curious. I don't know. I don't like it.
Ben just like has this like rolling notes tab.
Who?
Ben Smith.
Oh, he just uses this instead of going to the board.
Mm-hmm.
That makes sense. Yeah. Can you all see that okay?
I can shut the lights off if you need me to.
What?
I can shut some of the lights off.
I mean, is everybody okay with this? Because I'm gonna go back to it. So I put this together, and this is actually chapter 7 information, but I'm trying to fit it in now because we just got done with, we did autocorrelation, but the cross correlation, remember, you transmit a signal, call that X of T, and you receive it back in a radar pulse, call that Y of T. Right? Well, those two, since X of T literally created the second one, you know there's going to be something related. So if you do the cross correlation of that, you get a lot of information. It'll tell you exactly how far, or pretty close to exactly how far it is away the target is, even though in the signature that you receive, if you look at it just with your plain eye, it looks like it's just nothing but noise. The signal's buried in there, and the cross correlation function will allow it to come out, and it's done all the time. But there's something else. Have you heard the term matched filter? Anybody? A matched filter is really an optimal filter that maximizes the signal to the noise, and it is basically the cross correlation function. But there's one slight thing, there's a tunable factor, it's a scale factor. I'll try to explain this at least. That's the best way I can explain it this point. So for this, I'm going to tell you, when you're looking at this, we're used to the autocorrelation function, and from that, now this would be for a signal X of T. We could get just X of T, not cross correlate. We can get the power spectral density, and I'll define this in a second. It's going to be the Fourier transform of this. And if it's in the F domain, and the frequency just F, not omega domain, then it's a simple thing where you simply take this function and you take the Fourier transform of it. But if you wanted it in the omega domain, then there's going to be a 2-pi relationship between them. We'll get to that. For linear filtering, remember if you had input of a signal X of T, output Y of T of a system, Y of T was equal to the convolution of X of T with the impulse function of the system. Do you all remember this basically? Remember the convolution of an input gives you an output, right? As long as you have the impulse response. In the frequency domain, if you have X of omega times H of omega, you get Y of omega. You all remember that? That's simply, it's multiplication instead of convolution if you're in the frequency domain. And if you're talking about power components, and this is where I'm going with this, and you're talking about filtering anything, do you remember that if you have a band pass, band stop, band reject filter, or notch filter, you always have an H, or a transfer function, that you're multiplying some signal by to see how much passes or how much is blocked. Do you all remember this? Low pass, high pass, band stop. Those are the basic filters. But if it's power, then you have to square that transfer function. This is important. So we'll get to that. And one other thing, for a matched filter, now I'm getting ahead of myself here. For a matched filter, the impulse response is simply going to be it's really the time reversal of the transmitted signal, but it doesn't show up quite that way here. Let me go through this. All right, for this one, this is if it's wide sense stationary, here's a good way to think about it. This means simply the mean of X of T never changes. When you think about wide sense stationary, it's a pretty simple definition, but for the most part, it's as clear as it gets. If the mean of a process never changes, it's wide sense stationary. That's sort of a generally accepted thing. And I'm not an expert on this, by the way. I'm just leveling with you. That's the way we think about anything. And then this is the definition of the autocorrelation. Usually you just put tau in here. We use this definition right here. That's what we've been doing. I think everybody knows that. We ignored the T1 and T2. We just put in T and then T plus tau. Okay. So this, when you did like the mean squared value of the autocorrelation function, you didn't realize this, but that's the total average power or the peak in the curve, in the power curve. And we'll see this again. All right. When you're talking, something else I gotta say this. Power signals go on forever. Energy signals basically have a finite duration in time. However, when we talk a lot of times about power spectral density, we talk about a window in time where we're talking about the power. We're not talking about an infinite length of time. And that'll be more apparent later. We know that for any real process that if there's symmetry in the autocorrelation function, also the maximum of the autocorrelation function is at 0. If you wanted the mean squared value, and I think everybody should know this, the mean squared value of x, you simply let tau go to infinity and look at the value left over in the autocorrelation function, and that's the squared value of the mean. If there's a periodic component, it's obvious because there's a continual periodicity in the autocorrelation function. Now, this is kind of important. When we talk about power, remember I said, you're used to, if there's a power quantity, if voltage is associated with x of t, then V or current, either one, then V squared would be associated with the power or energy, depending on how you're going to use it. So the actual power term or power in a signal is 1 over 2t. The integral from minus t to t of the magnitude of x of t squared dt. Now that is sort of just a generic definition and has nothing specifically to do with circuits, but this is what they use in general in information theory and in communication. They just take any signal x of t. They don't have to say it's a voltage, it's a current, or it's anything. But the energy or the power associated with it is going to be the square of that signal integrated over a period and divided by a period, so it's an average. But that is power, average power. And there's something that is obvious here. There's a shortcut, and it's just that if you take the autocorrelation function at 0, that is the power. And they call it a density, power density. And the power in a process, and now here we're taking a look at something where tau is, or t is going to infinity, and here's where I gotta make a point. If you look at that carefully, what if x of t had a finite duration? Then the power in the signal would go to 0. Just think of a pulse, anything finite, right? If you take that and square it and integrate it, you're gonna get a finite number. But if you divide it by the 2t, by the way, can you all see this right here? If you divide that by 2t, as t is going to infinity, you got something finite divided by something infinite, it's going to 0. So in these type of things, we always talk about a limited value of t that we're interested in. But this, nevertheless, is what would be called the power in the signal. Now, this is sort of the generic definition of the power spectral density. And if you take the Fourier transform of x of t over, and you're going to basically take x of t, and this is the Fourier transform defined here, and I think we all know that. You take that, and then you square it, by the way. No, that's right. You square it. Now you've got something akin to an energy. You divide it by the period, or the existence, how long it existed. It's going to be over 2t, and let t go to infinity. In that limit, you get what's called a power spectral density. And it's PSD. Whenever you see PSD from here on out, it's power spectral density. And the units are watts per hertz, or watts per radian if it's omega. And it's a little abstract and confusing, but it'll become clear. I've got to ask you a question. When you did Fourier transforms, were you in the omega or F domain? Do you remember? Like, normally if you had, in the omega domain, right, there was always what, that 2-pi relationship that if F of omega was the integral from minus infinity to infinity of F of t e to the j minus j omega t dt, then if you went the other way, if you had F of omega, you'd have to integrate that from minus infinity to infinity times e to the plus j omega t d omega, but there would be a 1 over 2 pi in front of it to get back to the time limit. Do you all remember basically that? Is that the one you use mainly? If you did it with just F, since F, 2 pi F is omega, there's no 2 pi factor. That's why a lot of people like to do it. Did you do it with the F domain?
We did both.
You did both? Okay. Well, I'm used to the omega domain, but actually, in reality, it's probably better to just use the F for one reason. There's no 2 pi. Then you understand? You can't confuse yourself. Anyway, that said over here, the power spectral density for any, and this is basically the autocorrelation functions transform. Anytime you transform, you're going to have everything's strict real. There's no imaginary parts, and they're non-negative. They're symmetric. And basically, the energy, if you look over here, you'll notice he uses, if you integrate the power spectral density in the F domain, you don't have a 2 pi, but if you integrate the power spectral density in the omega domain, you have to get that 1 over 2 pi, and that would be the same thing as the expected value of x squared, or be the autocorrelation function evaluated at tau equals 0. A lot of this may not seem interesting or necessary, but this one is right here. This one, pay attention to. When we talk about the power in a certain band of frequencies, now remember the power spectral density right here, Sx of f or omega, is symmetric. So if you want the power in the frequency, say from 2 to 3 hertz, then what you need to do is integrate this power spectral density over 2 to 3 hertz, but you multiply it by 2 because it's symmetric on both sides. We don't integrate from -3 to -2. We just multiply by 2 and integrate from 2 to 3. We know it's going to have a power spectral density down there. All right, so here's the fundamental definition of the power spectral density in the omega domain. It's simply the autocorrelation function, and there's tau as a symbol, not t, and it's a transform, a Fourier transform of that, and that's it. And then to go the other way, and this is what I really wanted to just make sure I can tell you, you have the 2 pi if you're going to stay in the omega domain. You don't have to, but you should be very clear about that. Most of this stuff should be apparent to you. I think at least there's nothing new right here in terms of transform theory. You've had all this. So these are the pair that's spelled with the English spelling, by the way. That should be a Z. And if you take a look at the typical ones, you should know. If you have white noise, that's an impulse. By the way, when you look at the power spectral density for white noise, it's just an impulse. The only time, the autocorrelation function for white noise, the only time there's any value of the autocorrelation function other than 0 is at 0, when literally you're taking the value of the noise and squaring it at a given instant time. Remember, there is no correlation with applied sense stationary white noise. So in the frequency domain, the only thing it is, it's flat across the band. It's NO over 2. It's really, and that's just a scale factor for the noise. Here, if you have an exponential, this one's going to crop up over and over again. If you have e to the -2 magnitude of tau, like such, then the Fourier transform of that is going to be 2a over a squared plus omega squared. I had that one up there somewhere, I think. Do you remember this at all? Now, if you look at this, that's a legitimate spectral density, that's a legitimate autocorrelation function. Here, if you have something that's basically random and periodic like this, you're going to have something where that periodicity is going to be the frequency range over which the spectrum exists. And you'll have spectral lines where the actual, at the frequency components. Remember, both for sine and cosine transforms, if you had like cosine of omega naught t, the transform of that in the frequency domain, that's going to be what? It's going to be pi over 2, and then it's going to be a delta function at omega minus omega naught plus pi over 2 times delta of omega minus omega naught. 2 spectral lines, 2 delta functions. Do you all remember that for cosines? Or sines, anything that's periodic, sine or cosine, you get spectral lines that are clearly identifiable. But if the duration of the sine or cosine function, say you only got 100,000 cycles or 1,000 cycles, then you'll get a broadening. It'll be something like this. And that would be at omega naught or minus omega naught, but it wouldn't be a spectral line, it would be sort of a Gaussian curve. This is the one we did in the book. For this one, and it might behoove everybody to be attentive considering this a quiz. If you look at this function, can you all see this right? Do you all remember that? The mean squared value, just evaluated 0. If you wanted what the periodic part is, well, this one, there's 6 pi t. I'm sorry, the mean value, let tau go to infinity. You get the mean value, therefore the variance is that. And if we look at the transform, term by term, I tell you what, I'm going to forego that right now because I don't have time to do that here, but I will get to that. But we'll talk about taking the transform of this whole mess. The cosine is no problem, constant is no problem. That's a delta function. This is the one that's a little tricky because it's got a cosine and e to the minus tau squared there. All right. So if you wanted, if you said that you had just a density function, now notice it's in the F domain, not in the omega domain, has a value of 10 between A and B, but both for minus A and minus B, or I should say from minus B to minus A, as well as from A to B, has a value of 10. Then to get the mean squared value of the power in that, you would have to integrate over that band, and he puts a 2 here because there's going to be negative and there's going to be values of the spectral energy, spectral power, sorry, in the negative and positive F domains, and he would get this. And total power, this is for part 2. If you had this as the power, now see this one in this, this one right here, that power spectral density function, that is actually e to the minus a magnitude of tau. And if you look at that, and you want the total power, now you can see that this integration is something that's doable. You actually can do it a couple ways, and you can get that. But you can also take this and go back and just get the autocorrelation function that would be associated with this power spectral density and evaluate it at tau equals 0, and you'll get it. Finally, let's see here. This is a little new. that interested, I'm just gonna mention this. You're used to H of T and H of F or H of omega. An impulse response associated with an actual value of H of omega or H of F. And that would be something, that would be the filtering, you might say, operation. Where if you had X of T, you could also go and transform that to X of omega and multiply it by H of omega to get Y of omega. And then if you wanted the time domain function, you could take that Y of omega, take it, do the inverse transform, get Y of T, the output of that. That relationship you should know very well. And you can do it both in the F and omega domain. Now, when we're talking about power, it's always going to be squared operators. So if we had the input spectral density of a system, and by the way, spectral density doesn't have phase involved in it, and it's basically immune to time delays. So the only thing you're really talking about is something that's going to be a magnitude, strict positive magnitude function right here, no imaginary values. If you have that, you have to actually square the transfer function to get the output, Sy. So remember, if it's voltage, like V of omega, you multiply it by H of omega to get the output, V, the output of omega domain. But if it's power, you have to square the transfer function. That's one important point. Something else that I didn't mention yet. If you want the output's autocorrelation function of Y, you have to take H of tau and convolve it with H of minus tau, or I'm sorry, this is multiple. H of tau multiplied by H of minus tau times the actual input's autocorrelation function. This is a little bizarre right now, but you'll see why. And by the way, I should say this. This function right here will be convolved with that function. It is convolution 3 times, but it's really the first function right here, convolve first times the input. All right, let me mention this last thing. I'm going to have to do I'm going to have to show you some problems to really have you appreciate this. So this, if you look at this problem, and we had this transfer function, does everybody know where that came from? Let me ask you this, if you're looking at this, can you all see that, by the way? Right here, my green. So it's 1 over 1 plus 2 pi FRC. Do you know what that is? That's a low-pass filter, isn't it? Evaluated at omega equals 0, you get 1, right? As omega goes to infinity, you get 0, right? It's a low-pass filter. And I'm going to make my point. I'm not going to belabor this too much, but let me do it right here. If you have an input here, plus and minus x of t, and you had a resistor here, R, and you had a capacitor here, C, we'll do it in the omega domain, and I wanted the output voltage here, call this Y. With me? Now, we'll do this. First, we're going to get a transfer function. So we're going to go to the frequency domain, and this will become, and I'll get out of your way in a second, an x of omega, and this will become a capital Y of omega. So I'm going to assume we're doing transform domain. After that, R remains R, but C gets an actual value of impedance of 1 over J omega C. Everybody remember the capacitive reactance, 1 over J omega C? Now the output of that thing, if I looked at Y of omega, it would be the input X of omega, and then you would take this output impedance, 1 over J omega C, and divide it by 1 over J omega C plus R. Get out of your way. Y'all follow me what I'm up to? That's a simple transfer function relationship, right? Now, if I take this, and sure enough, the eraser is right kind of here, I think, over here. I'm going to go ahead and just make it look like what's up there. Multiply top and bottom by j omega c. And then you get did you all see that? Now this, if you replace the omega with 2 pi f, is what's shown right there. So here's my point. If I give you the power spectral density of this function, that's x of omega, but if I square that value, do you all follow me on this? You square that value, now I have the actual power. I don't have the autocorrelation yet, but power. And if I take a look at that, and I would multiply that by the square of this, as a matter of fact, I'm not doing this as well as I'd like to. If you have y over x of omega, that is the definition of h of omega. And that is what I'm showing there. But if you take the magnitude of that right there and square it, then you could take the power spectral density of the input signal and multiply it by that, and you get the power spectral density of the output signal. That's the only point I'm trying to make here, and I'm going to finish in a second. So if the input is simply noise, then the output power spectral density will be simply a constant, the noise, NO over 2, times that transfer function. And then, if you take a look at this, I'm just going to stop here. If you take the inverse transform of that, you end up with this. Now, I remember, I'm not going to keep going that way, but remember how I said e to the minus a magnitude of tau went to, and it's actually 2a over a squared plus omega squared. So that would be the transform pairing relationship. But you can see that this has the same exact shape. It's got an e to the minus t squared, or e to the minus t, pardon me, divided by RC, which is just tau. And it's the inverse transform of that. And that would be the power, or the noise power in the output. I'm going to have to stop there, but I'm going to tell you where I'm going with this. And you're going to see how what looks like a confusing thing. I'll be talking about maximizing the signal to noise ratio. And let's see if I have that one thing in here. You know, you remember before where on Denny's slides, he showed a transmitted signal that was basically a sine wave that had maybe 1,000 cycles, something like this. It hits a target, reflects back, and there's noise added, and the signature gets broadened a little, and there's all sorts of things. And it looks like this. And by the way, a real radar signature return, if you look at raw data, even if you strip out the high frequency component, it's going to look like noise. You can't see any signal in there. But once you go ahead and take that signal, you go from A to D, you digitize it, and then you run autocorrelators and something called a matched filter, which is an autocorrelation function with a tuning factor. All of a sudden it becomes very apparent where the target is. And usually you just take the magnitude of this thing right here. And you can get this distance right here, from here to here. That would be the time delay to the target, from the time the radar signal is transmitted until the time the reflections are seen. And that time delay is twice the distance. So if you take C times this time delay, where the peak occurs, and divide it by 2, you get the exact distance of target. That's the idea. Radar is so much more than this. This is just the tip of how radar processing really works. But it is important to at least understand. Last thing I'm going to say, and this is a real signature. this is actually a cross correlation function. But if you take a look at a real radar, if you take a look at the power spectral density of radar, you're going to get something where sorry, the autocorrelation cross correlation function of radar returns. I'm going to show you something. You will get all these peaks like this all over the place, and the idea is you want to maximize that peak that is associated with the radar return, the actual return. And the way we do this is there's weights, and they're called windowing. Have you heard of like Hamming windows and stuff yet or no? Well, you will. I'm not sure, probably in communications, but boy, this is another lecture, and I'm trying to just at least give you some information. I'll stop there and give you a quiz. That's what you really want. I'll give you some specific problems, but then I'll make these slides available. You'll find out that the slides themselves